I'm going to talk about the fractal dragon, but I'm also talking about these Truchet curves. And so I started off this project with playing with Truchet curves, which is very well-known, really simple design, because you take one tile and you repeat it over and over and over again. And then, so in the background, you've got this kind of Truchet design, which is called the Smith Truchet tiling. It's just a tile with two quarter circles on it, and you can arrange it in lots and lots of different ways. You know, Truchet, well, I think Truchet was studying these, several hundred years ago, but he was looking, if you look at his original work, it's sort of a tile which has one half is down the diagonal is black, the other half is white. But really any kind of very simple tile which is repeated tends to be called a Truchet tile. This one is called a Smith Truchet tiling, which was sort of popularized, I don't know, probably in the 60s or something by Cyril Smith. I'm not sure. Anyway, it's become a very popular design. So by the way, the talk I'm giving here, this is the little QR code for the talk. So the talk is somewhat interactive. So if you want to, you can go and look at the webpage now or afterwards. The code, some of the code is, because it's you've got this basic Truchet tiling, and I saw it referred to as a space filling curve. Normally, at least in mathematics, you don't really call something a space filling curve unless you have a sort of iterative process to really get it to fill all space. And I didn't, although I've seen it referred to as a space filling curve, it didn't seem that there was a method that I could find in the literature actually giving an iteration. So I came up with a method of iterating this Truchet design, get another Truchet design, and then it turns out that you get the fractal dragons, which has also been known for since 1966. I think John Highway came up with this idea of fractal dragons. So it's a slightly different way of thinking about the sort of generation of fractal dragon curves. And I just want to talk about it, and you can look at this, look at the web page now or later. And I'm going to ask Melina to be my assistant going to the next page, so I don't have to be crouching down. Oh yeah, so by the way, if you go to the this thing, you've got lots of controls and whatnot, and you can have a go at, maybe I'll show you. So yeah, can you click on the more iterations, because that oh yeah, good, you've already got it loaded, haven't you? If you want, you can click on these buttons to have some of the examples of different kind of things I'm going to talk about, and there's more examples here. If you click on these ones, these have more iterations, and there's loads and loads of all of these things. You can I don't know if you want to like change, I don't know what, change the line metric or something like that. So this one, and now we've got a pattern. You better change the line width, because oh yeah, this one you can see the line width. Click on the line metric here. So this has got you know, the metric tells you how far a point away is from another point, and the usual metric is the Euclidean metric, and it's square root of the sum of the squares of the components of the vector, whatnot. So you get a circle. Here is this sort of this is a supremum metric. So this thing here is a kind of square shape, but really it's all the points which are the same distance from the corner under the supremum metric. If you touch the this one here, you're going to get the taxi cab metric. And let's try a different, I don't know, try a different tile orientation. So, you know, my tiles each, so here, the tiles are all the same, except now I've added color as well. So the basic concept of the Truchet tiling is to have, you know, they're all the same, identical, but you can see patterns in them. So I wanted to add color to bring out that pattern. And, you know, the, because it filled, so let me, why don't I ask you to go to the next slide. So here's my thing with it, you know, this Truchet pattern with its different orientations. And of course, it's just the same pattern repeated over and over and again, but you can, you know, your eye sees these circles in it. And this is just sort of random. It's not actually really random at all. You want to change the orientation. And if you change the scale, do you want to change the scale over here and make it, yeah, that's it. And change the orientation again. I don't know if you can see, if you change it quite fast, you can see that it's actually very regular and it's not really random at all. But I thought that was kind of fun because on some scales it looks random and some scales it doesn't look random. And this is just, it's kind of all coded in WebGL and some JavaScript, but mostly this is all done in WebGL. And one random method, the simplest random method is not random at all. You just take the dot. So I put my little remark dot will tell you that it's the the orientation of these is just basically taking the dot product of the tile coordinates with a vector. So the vector goes in some particular line, and I take that modulo 2. So as I move along lines, you kind of get things rotated as they kind of match up along certain lines. So, but I thought that was fun to see that, especially when you move the orientation slider, and you can kind of suddenly you see that structure, but when you look at the still image, you don't see the structure, but suddenly when you see it moving, you see, oh yeah, there's a vector moving around there. So it's kind of, I thought that was fun anyway, that it's not actually random. But anyway, okay, so let's go to the next. So this is basically what the tilings are that I'm interested in. Next slide. Now I wanted to add colors to them. And oh yeah, the other thing is, in order to produce, so I'm going to talk a little bit about my implementation in the WebGL. I'm using the GPU just because it was, well, actually, that's what I spent more of my time thinking about recently. So I did write a program to sort of draw these pictures, about a year ago, and then I wrote the paper that's on the archive. But I just filled, although I was also using WebGL at that time, I didn't have a good coloring method. My coloring was all done in JavaScript, which told each tile what to color. And for various reasons, it didn't work very well. And for this talk, I came up with a new method of doing everything in the GLSL, which works better for iterating very many times. And in order to do that, in fact, at the moment, it only really works for tilings where I have a formula. I think that's probably possible to get sort of formulas in random case, but it's much easier to get formulas in a regular case. So in this particular case here, each tile has a coordinate. And so if I take the sum of the coordinates and I add them up and I take that result modulo 2, I'm going to get an alternating, let's see, the color. If you move the color a bit, I think if I move it, yeah, move it back down again so it's all white, all yellow. Maybe when you've lost the color, you can see more easily that each tile, this is my 0 direction, this is my 1 direction, so they all alternate between. I got 2 orientations of tiles. The basic tile, the tile rotated by 90 degrees, and I'm going to just call those 0 and 1. So when I say the orientation is a number which is 0, 1, it means it's rotated by either 0 or 90 times 1. So you can see how these all alternate, and we can look at different patterns. So when you go through the other ones, I get little formulas for them. So of course, everything's the same orientation 1. Here, that just depends on the x coordinates. So they're all that direction, all that direction. What else have I got? This one. Oh yeah, this is a funny thing. The psi, this is a joke, I guess. So here, x.5 just means x plus the x coordinate plus 0 plus a half. It's the sort of thing students might write, but I thought it was funny. And because I've got my 0 tile is here, or maybe I think my 0 tile is there. This, I want it to be symmetric about this point here, so I have to add 0.5 to get the sign to be either a positive sign or a negative sign, and not 0. So that's just whether those things are equal signs. So this gives me this kind of flower pattern. And what have we got next? Just this kind of everything is rotated from the previous picture. And I guess you could probably get formulas for other things, and probably it's possible to get formulas for random things, but it just those are just the examples I've done so far with formulas. If you click on the orientation button, I think I just wrote everything that I just said now, but that's just in case I forget to say anything, or if anybody's looking at it later on, they can click on pink things and it maybe shows some more words if I forget to say anything. Why don't we go to the next? Oh yeah, by the way, change the color again. So so I've got my different colors for these paths. previously, like last year, I had this program where I'd kind of followed around in the in my JavaScript to see, what tile is next to what tile. But I wanted to do something in the GPU, which does everything all at once, zam, bam, zam, the whole thing done all at once. I don't want to like see what's next to what's next to what, because that turns out to be really, really slow. So as well as having a formula for the orientation, I need a formula for the color. So let's go for the next slide here. And so here we've got a formula. It turns out that in all these examples, you can get formulas for the colors. So before I said that there is each tile has a coordinate, XY coordinate. I also give coordinates to the edges, which I'll describe on the next tile. But if you click through these buttons here, there's a formula telling me, and if I change, you can get more colors by moving the color thing. It just changes them. I don't know. You can change the scale as well to see the thing on a bigger scale. So if we change this, I don't know, it's just fun. Okay, so so there's all these different colors, but now my color, instead of being determined by following from tile to tile to tile, I've got a formula which is going to be really useful when I iterate, because I don't want to have to follow around from tile to tile to tile when I do hundreds of tiles, because it's just going to take way too long. So let's go to the next slide. Okay, oh yeah, and I wanted to tell a little bit more about the implementation. So basically, I assign a color to each edge of the tiling, right? And let's click on let's see this button that says tile, click on that one, that little circle there. So each tile has a number which we use for just referring to them and doing the computations. Click on the edge thing. So here's these, I think, these are some this one is supposed to be here, that one's supposed to be there. I think if we move, if you make the page full screen after you've loaded it, it's rearranged. I should have probably changed my JavaScript or something, because the background is in the WebGL and the foreground is in just JavaScript and CSS, but they're kind of not quite updated one with respect to the other. And if we put click that thing here, now we've got the labels for the, this should be up here. And if you click on the last button, there's a sort of relationship between them. So I don't know if you can see that, but basically it's saying given any square, you can have coordinates for the edges, so you can do all your computations with them. And we assign a color to each edge, and if we use that, see that little slider there, so just move it all the way across, so that just fills in the edges. So that's just how I do. So each square is actually taken, in typical thing to do when you're doing programming and some WebGL, GLSL, is to just start programming kind of square by square by square. So each square does the same thing, but with the different colors that get assigned to its edges. This has got a random color scheme. If we use the, let's see, if I click on that little first, see that little dot there? Now this is now using those formulas we had in the previous slide, so that all the colors are all nicely consistent. Okay, let's go. What did I click on? What does my note say? I think it doesn't say anything extra. So let's go on.
One quick question.
Yeah.
Josh says it looks like the sign x.5, not y.5, is a shifted version of the sign x.5 equals y.5 pattern. Is the amount of translation significant, or an artifact of the scale, or something?
The 0.5 thing. Yes. Sorry, which one was?
Apparently we had 2.5 patterns.
Yeah.
They look like a shifted version.
Oh, we'll go back to it. They weren't actually shifted. They were all just, the difference was everything was rotated. So one of them is like a sort of, you might call it a dual of the other one, and that every single tile is from one is rotated from the other. So if you go back, let's see. So if we click on the last two buttons, so or maybe you want to go, but anyway, if we click on the last button, every single tile has been rotated. Okay, so the previous slide showed the formula for the the direction, and this is just, of course, my tile edge coordinates are just in a sort of constant. Then, you know, I've shifted my coordinate axes for the tile indices. So now my, probably I took some sort of absolute value of LOM because I've got a lot of symmetry in this just to make it easier. But anyway, why don't we go to the next slide? Because, okay, let's go to the next one because we've done that one. Oh yeah, now we're going to talk about hinged tiling. So how do we go from, how did I want to iterate my Truchet tiling to get to hinged tiling, to get to a fractal tiling. So when you turn this thing, so turn it like that and just carry on turning it. So this is a typical example of a hinged tiling, and you can take it back to the middle, and then you can take it in the other direction. So in fact, there's two possible choices of where the hinges are, right? So we've got two possible different ways you can rotate things. What I'm going to the next slide. So if you bring it so these blue areas are square. So the blue, do you want to stay on this slide 1 minute? So take it to about halfway there. So now the blue things become square. So this is my iterative procedure. I make the whatever negative space into a square, and then suddenly I say it's not negative space anymore, it's another square. What did I say? What was my note? Remind me what my note is. Oh yeah, so there's loads of references on things like hinge tiling. So this is like the most simple possible hinge tiling you can have. There's other ones you can look up. When we go forward. Okay, so try this one. So try the turning this one. So we turn it, but then when it gets to the middle, instead of folding it up again, I'm going to carry on going, and we open it out some more, and we open it out some more, right? So this is my fractal process. And now the width is to add these things here. So when you go back to 0, whatever on the turn, let's see, do we go, yeah, fold it all back up. Oh, we've got the other way. When you fold it up to the middle, oops, the daisy. Okay, anyway, so you start off with this kind of Truchet tiling. I've just taken the circle one, you open it up. So let's see, open it up so the yellow bits are squares. And then if it opens up a tiny bit more, just make it a tiny further off to the right, that slider, I think, or move it further. Yeah, and when you move it to this way, that's it. And move it further, a little bit more. And then I'm going to fill it in with these things here. And there's a unique way of filling those in. If you see the width too, that's supposed to add these little things here where you can sort of see how if you closed it up, things are just staying connected in the same way as they were in the first place. So there's a unique way to fill the thing up. And if you put the width 2 to be, if you move it right up to there, then, and now let's see, you want to move forwards with this turning thing, you end up, so this is my fractal procedure. I start off, or whatever, my iterative procedure. I start off with my Truchet tiling, and then I just do hinge tiling, and I'm going to keep on going and going and going. When I first did this, I didn't actually know what, I didn't know what I was going to get. I thought, well, obviously it's some sort of, seems kind of fractal, but I didn't realize I was going to get the fractal dragon, but I kind of recognized them. Let's go on to the next. Oh, do I have to show, hold on, go back to the note. What did I say for my note here? Is there anything? No, just go on to the next one. Sorry, it's just, I can't remember what I'm supposed to say. Is this my cards or whatever? Okay, right, so here, I don't know, when do we turn it? See if we go, you can go just, so let's look at, so this is, as I said, there's 2 different directions to turn, right? I've called those directions 0 direction or 1 direction. When we click on these example buttons here, so that is the one we already have. Let's click on this one here. This means turn the anti-clockwise and the clockwise direction. So each of these are going to be different sort of binary sequences, which are going to give different results. Also, just to demonstrate, if you click on the metric button, you can see just how it looks if it's got a kind of thing that goes, instead of going in an arc, goes to the middle and back down. Or if you can, like this one, you get this thing, you can click on the fill button. So lots of nice effects. So, and yeah, funny, just, I don't know. Let's go to the, oh, what did I click on for notes? I click on my notes somewhere. I have a, yeah. So this thing I wanted to mention because I thought this is my main problem I solved. If you scroll this down a little bit, I was talking about how do I find the color. So when you're doing something in WebGL, I want to take like a square and say, what is the color of that square going to be after a lot of iterations? And I don't want to like try to follow around a whole lot of stuff. So it turns out that there's, I thought it was an amazing formula. I was very pleased to find this anyway. If I've got a formula F0 telling me my initial colorings of my edges, if I want to find out what those edges colors, okay, I have to relabel everything in a kind of sensible way each time I get a new grid on a sort of smaller and smaller scale. But there's this recursive formula to tell me what my edge color is after each operation. So I'm just going to apply this funny a sequence of, I call them T and R, and they're taking the coordinates, they're adding or subtracting and dividing by 2 and taking the floor, and just applying a sequence of those operations to the vector over and over again, and then apply the original color function. So that means I can do all of this without having to do any JavaScript following things around. I can just apply this iterative thing, which is sort of, in a way, iteration can be kind of slow, but on the other hand, it's doing it in parallel. So each square does it sort of at once. So I don't know. Anyway, I think it's definitely much faster than doing it the other way, although maybe it's still a little bit slow. I think the slow thing is to actually do the compiling. Like when GLSL compiles itself, it doesn't like iteration very much, but once it's compiled, it's okay. Okay, let's go to the next slide. And we're kind of running out of time. So when you click on some of these examples here, so these are some of the different kinds of fractals you can get with the different, so you've got different sequence of turns. When we move this turn, I call it turn here, I don't know, turn iteration. So you can go to see, and this one, I've just started with one little edge, not a whole circle. So you can like go to sort of maximum of that sequence or the minimum. Of course, it's not actually really fractal until you've done it infinitely many times, but at least you get a good approximation for something that looks pretty fractal. I think I'm running it up to 14 iterations. And what does coloring do? Oh yeah, right. So the coloring, instead of looking at just one of them, looks at a whole load of them, and they all interlock together. They're like a sort of tiling. And what did the last coloring do? The last button there, I think that does a sort of underlying, the underlying sort of first 2 steps of the procedure, and then shows sort of where you get to on top. So yeah, that's probably too small, isn't it? Maybe make it bigger. So it's just kind of show, I don't know if that was a good. The quality of that is not so great, is it? Let's go on to the next slide. All right, so I wanted to talk a tiny bit, which I might not be able to get on to all of the slide, but what I also wanted to show that is a nice thing to be able to do with the GLSL, the kind of GPU approach, is that you can vary the number of iterations across the screen and sort of give a feeling of iteration while only showing one image. So, instead of showing just the first step or the final step, you can kind of show a little bit of all of the same thing on one thing. So let's see, just when you give me some example, when you click on it, was this the first example? So 2 ideas are in here. One, so when you go back to the second picture here, this has iterations sort of stacked on top of each other. So you can see how one iteration is related to the previous by sort of following them around. I guess if we bury this stack, where's this iterate? Yeah, if you use that iteration. So the top, yeah, that one, right? So you can kind of sort of see how each step, oh, this is this had a, yeah, no, I think it's not perfect, but anyway. Anyway, you can sort of see how one grows out of each other and kind of look at how they are sort of all interrelated by having this kind of stacking option. And the other thing, let's see, maybe go on to one of the other examples. Yeah, this one I've got variable iteration. So if we change my variable thing, you can see that some of them are more, it's sort of, yeah, it's a bit buggy. It probably has something too big or some. I think if it tries to iterate outside the range to which the iteration is running for, it will not look right. So I probably should add something to limit the size of some variable. But this is still a baby program. This is written from scratch over the last month while I've been moving house. So it's definitely not perfect. But anyway, yeah, the idea of the variable iteration is you can sort of see this version here in the middle and see versions which are, let's see, if you're on the, you can also scroll up and down on the version that you can have more controls of, but you can kind of get an idea a little bit of how further out iterations are related to this one. Also, you can change, so you see the operation sequence, we can change that to something else. I don't know, when you try deleting and replacing by 0, 1, 0, 1, 0, 1, 0, 1. Is that going to delete? Doesn't look like it wants to do anything with it. Wonder why not. Is it just slow? I'm surprised it doesn't. Never mind, if it doesn't want to do it. Anyway, there's lots of different examples of being able to see iterations at the same stage. I mean, sorry, iterations at different stages on the screen to sort of try and convey the idea of the variation. It's only that doesn't do it. Never mind. I don't know. Do you want to go on to the next slide? The only thing is I probably don't have any time left. I was going to talk about fractal dimension, and I know I've got like 1 minute left or something. What I wanted to say is fractal dimension. So when something's fractal, it sort of tells you a little bit about how that thing is related to each other itself at different scales. And like a square, when you divide the square and scale it by half, the number you need is squared, right? So, and if we move that scale along here, however you do it, you've got a number here that's 2, which kind of tells you how the big square is related to its small ones under the scaling process. And there were more examples, but I don't think I can really talk about those, except that in any example, you've got this number here. Okay, this is the simplest kind of fractal, which is self-similar. There's, you know, in a very sort of rigid way. And you know, you always get this power here, which is telling you about fractal dimension. If we maybe just go on to the next slide. Let's see, let's go on to the next slide. I was going to talk about the fractal dimension of the boundary, but I think I'll just say, so if we tell you what, move the iteration slider all the way over here, right? So this is my basic fractal dragon. I mean, there's lots and lots of different fractals. This is the one we keep applying the same operating over and over and over again. Let's go back to and in this picture here, it's each color is split into 2 regions. So there's this yellow one here becomes these 2 yellow ones here. If we move this yellow, move that slider right back to the beginning. So what I've done in this picture here is to show, gosh, actually maybe go back to the previous slide. I think maybe it's easier to slide. In this slide, click on the split button. So the split thing here, click on the third dot for the style. Okay, and now I want you to slowly move the iteration button. And now we stop about here. So go back a bit. So this is supposed to show how each step is twice the previous one. So this block here becomes 2 blocks here, right? but the scaling difference is by √2. So this is √2 of the size of this thing, just like the triangle. And this thing is telling us that actually the whole curve is just got normal dimension 2. Its fractal dimension is also the same as its ordinary topological dimension. So the whole thing is not really fractal. It's this boundary that's fractal, which I probably don't really have enough time to say, but it's still interesting if you move this iteration thing along at each step. So let's see, so stop when it got there. You can see this long thing here kind of here and here, and move it again. And that sort of shape that goes around the corner is seen there. And at each stage, you see 2 copies of the tile at the previous stage and the next one scaled by √2, so it means at least you can very easily see that the dimension of the whole of it is just 2. It's just a whole number, which means it's not really fractal. And I don't really have enough time to talk about the fractal dimension of the boundary, and I'm sorry about that. But you can look at the web pages and hopefully read along for yourself.